I normally don't do a lot of examples in my videos, but I thought this would be a really nice time to just pause for a second and take a look at some examples of these derivative rules that we've been looking at. So we're going to take a look at these in a couple of different ways. We're going to take a look at some examples with some unknown functions where we just have information about the derivatives of those functions. And we'll look at how we can use the operations addition and subtraction with constant multiples to just combine these things. Then we'll take a look at some actual function types that we know, power functions and exponential functions. And we'll try and mix those up so we get a good feel for how things are working out. So let's dive into this. Let's start off with some unknown function types. What I mean by that is we just know a little bit about some derivatives. So we've got some function f that at least it's differentiable at the value 4. And the derivative at 4 is -1. And we have the same kind of thing for g. G is differentiable at x equals 4, and specifically g prime of 4 is 10. So now we have some combination of these two things, and we want to differentiate this. We can say then that s of x is the derivative of 3f of x minus 2 g of x. Now, you'll notice that we have this difference of functions. So we can split this thing up, and we can say that's then the derivative of 3f of x minus the derivative of 2g of x. And then suddenly we can also look at these coefficients, and we can say, well, we know that coefficients get factored out. And so suddenly we have 3 times the derivative of f of x minus 2 times the derivative of g of x. Or if we want to write that a little bit easier, in general, we have 3f prime of x minus 2g prime of x. So that's s prime of x. If we want to find s prime of 4 then, that's going to be 3 times f prime of 4 minus 2 times g prime of 4. And conveniently, those are the values that we have. This is -3 minus 20, -23. Done. All right, go ahead and pause the video and see if you can recreate this kind of thing on this second example. We, again, are going to find s prime of 4, but now we have a different, oops, this is supposed to be t prime of 4, sorry. But we have a different function here, right? Different combinations of f and g. So see if we can differentiate this t function by using our derivative rules for f and g and combinations of those things. Pause the video and we'll see what we get. All right, let's talk through this one. So hopefully this is where we're at. I'm going to rewrite these fractions with fraction coefficients instead. Instead of saying g of x divided by 3, I'm going to say this is really just 1/3 times g of x. And then same thing here, I'll just pull out this fraction of 2/5 to make it a coefficient. It's going to make things a little easier for me. So that's all I've done in this first step. Then I notice I have some sums and differences that I can split up. So I'm going to look at the derivative of each of these terms individually. The derivative d over dx of 1/3 g of x plus d over dx of 2/5 f of x minus d over dx of 10. For these first two terms, we have some coefficients that we can factor out. So that's what I've done. And then also we have a nice constant function. And we know what the derivative of a constant is. It's 0. So now we've got 1/3 times g prime of x plus 2/5 times f prime of x, and that means that t prime of 4 is going to be 1/3 g prime of 4 plus 2/5 f prime of 4. And again, those are values that we know. This is 1/3 times 10 plus 2/5 times -1. So we have 10 over 3 minus 2/5. And what is that? That's 50 over 15 minus 6 over 15. So we're looking at 44 over 15 as our derivative there. Check my arithmetic on that because it's not always great, but that's what we've got. Cool. All right, let's take a look at some examples with power functions. Here's 3 of them. Go ahead and just try these. Maybe we'll start by rewriting these. So I'll rewrite all of them just so we can see how this goes. 5x to the 6 minus 10x squared. And when I say I'm going to rewrite them, I mean I'm going to take this root and write it as an exponent of a half. Similarly, I'll rewrite my second one. I'm going to notice this is a negative exponent. I'll factor my coefficient out. So this is really 5/3 times x to the negative 2. And then similarly here, I have 3/4 times x to the negative half. Negative exponents are really things in the denominator. That square root is an exponent of half, so that's what we've got. And then on this one, I'll rewrite that last term. 14x plus pi squared minus, this is 2 times x to the negative. The fifth root is an exponent of 1/5, and then we square it, so we'll multiply that thing on there, so we have an exponent of negative 2/5. Cool. All right, go ahead and pause the video, see if you can differentiate these things. It shouldn't take too long once we remember how this power rule goes, especially when we're working with things with coefficients and all that kind of stuff. Okay, let's jump into it. If you haven't done it yet, for real, pause this and just do it. It's not going to take long. Okay, here we go. So this exponent is going to come out front. The coefficient is going to stay as a part of the coefficient and get multiplied. So we end up with 30x to the 5, because remember, we subtract 1. We'll do the same thing here, bring our exponent out front. So now we have minus 20x to the 1. And then we'll bring our exponent out front. We have plus 3/2 x to the half minus 1. That's negative half. If you'd like, you can rewrite this as 30x to the 5 minus 20x plus 3/2 square root x. This negative half is really a square root of x in the denominator. So there's our first one. For our second one, we can do the same kind of thing. Bring these exponents down and subtract 1. I'll have to be a little bit careful here with the signs, right? So when we bring this exponent down, we really have negative 10/3 x to the negative 3. Notice our negative exponent gets more negative. And now we have minus 3/4 x to the, oops, sorry, not minus 3/4, minus 3/8. We're bringing the negative half down out front. And then negative half minus 1 is negative 3/2. And again, you could rewrite this as negative 10 over 3 times x cubed. This negative exponent is in the denominator. And you could do the same thing here. Minus 3/8, and then with this square root of x cubed in the denominator. This negative 3/2 exponent is a square root of x cubed. Since it's negative, it's in the denominator. And so that's what we've got. And our last one, we can do the same kind of stuff on here. Notice this is really an exponent of 1. We'll bring that down and subtract 1. So we just are left with 14, x to the 0, or 0. Be careful here. This is not 2 pi. Pi is a number. So this is a constant function. So I'm just going to say plus 0. Maybe I tricked you on that one. Maybe not. I don't know. And then I'll bring this exponent down out front. I've got plus 4/5 x to the negative 2/5 minus 1. That's negative 2/5 minus 5/5. So what's that? Negative 7/5. So this is 14 plus 4 over 5x. That's a fifth root of x raised to the 7. Let me clean that up because that looks kind of gross. If you want to just leave this as 14 plus 4 over 5x to the 7/5, that's fine. I normally get pretty comfortable with trying to move these negative exponents down into the denominator, but sometimes writing things back in roots end up being a little bit more ugly than they're worth. But that's what we've got. So no big deal with these power functions. We can get used to those pretty quickly. All right, lastly, we'll look at a couple of examples with some exponential functions mixed in there. So let's take a look. All right, so we've got a couple of exponentials floating around here. We know that exponentials just stay themselves, but now we have this coefficient of 3. Don't worry about it. We can split this thing up into the derivative of 3e to the x plus the derivative of 9. So we'll split this across the sum. And then we can say this is really 3 times the derivative of e to the x plus the derivative of 9. So we'll bring that coefficient out front. What we'll really see here is that this is 3e to the x plus 0. So this term just stays 3e to the x. That coefficient on it doesn't really impact things. This second one's kind of tricky. Take a moment to think about this one. Notice the difference between these two terms. Go ahead and look at how they're written differently. Pause the video and see if you can figure this one out. Hopefully you're pausing it. Pause that video. Okay, let's go ahead and do this. What I want us to notice is that this is actually a power function, x to the k, right? Our variable is in the base here, and our exponent is a real number. Now, it's not a fraction or an integer, but e is a real number. So we're going to bring that down out front and subtract 1. So we have 6e times x to the e minus 1, I guess. There's not really a nicer way of writing that, so I'll leave it like that. And then this one is an exponential function, so we know it's going to stay the same. So we have 6e to the x. So just notice the difference between exponentials and power functions. It's all about where the variable is, x. In that first one, x is in the base, and in the second term, x is up in the exponent. So if you have your variable in the base and a real number in the exponent, that's a power function. We use the power rule. If you have a real number in the base and the variable up in the exponent, that's an exponential function, and we'll have to deal with it differently. All right, I think that's all I've got for these examples. Hopefully that's helpful just to kind of sink your teeth into, and we're going to move on and start looking at more operations between functions. We're going to look at how do we multiply functions together and find the derivative of the product, and then how do you divide two functions and find the derivative of the quotient. And from there, we'll be able to start working towards more and more function types that we can get derivative rules for.